So in this video, we're going to examine some of the problems out of section 1.7, testing them for symmetry and finding their intercepts, okay? So I gave you an assortment of the odd problems. I'm going to look at a couple of evens. We're going to start by looking at problem number 14. Here we are asked to take a look at y equals 1 over x squared, okay? And with that, we want to test the symmetry. Right off the bat, you should kind of suspect that since the x term is being squared, it's going to possess that symmetry about the y-axis. Now, legitimately, we should run the test. That is, we should replace the x with its opposite, and in doing so, we're going to check to see what that ends up giving us. So we replace x with its opposite, which effectively is negative 1x times negative 1x. Which comes right back to where we started. So that's fine because that demonstrates the symmetry is about the y-axis. Okay. Now let's look at the intercepts. If we want to find the x-intercept, we set y equal to 0. If we want to find the y-intercept, we set x equal to 0. So setting y equal to 0 gives us 0 equals 1 over x squared. Cross multiplying x 0 times x squared is 0, which leaves us with this statement 0 equals 1, which is not true, and therefore there's no solution, and therefore there's no x-intercept. To check the y-intercept, we let x equal 0, and replacing x with 0, we get 1 divided by 0, which is undefined, which again is implying no solution, which is again implying no y-intercept. Okay, so if we want to take a look at this as a graph, we'll go to our calculator, take a look, feed that in. We should support those ideas that was suggested here. Okay, so we go in and we key in y equals 1 over x squared. Okay, so it's 1 divided by x to the second power. Okay, we got that extraneous term there. I'm just going to delete that. Okay, we're going to enter that. Okay, that's just y2. I'm going to come out and delete this y1 because we don't need that anymore. And we're going to look at the graph. And looking at the graph, here we see, okay, there it is. It's never going to reach the x-axis on either side. It's called asymptotes, so it gets closer and closer. If you want to look at that a little closer, you can zoom in, and you'll see that it's never going to meet the x-axis. It's never going to meet the y-axis. Okay, so there's and it does have the notion of the symmetry. All right. All right. Now let's look at another one of the problems that we're going to test for symmetry and to determine its intercepts. Okay, we're going to look at number 20. X is equal to y cubed minus 1. So the first thing I'm going to do is replace y with its opposite. And the same thing as in the previous problem, that is negative 1y cubed, which again is negative 1y times negative 1y times negative 1y, which effectively is negative y cubed. Now, that you can see does not return to you the original problem. Okay, so what were we testing for? We were testing for symmetry about the x-axis. So since the net result is not the same as the original, there's no symmetry about the x-axis. Okay, and it would be nice if I could just say, well, when I pulled out that negative, I got a negative inside of here, which would be effectively saying, oh, I'm getting back the opposite of what I had, but I'm not getting that either. So there's no symmetry with this at all. Okay, no x-axis symmetry and no origin symmetry. Okay, so we explore to find the intercepts. Again, if I let y equals 0 in my original equation, I get x equals negative 1. Okay, that's easy enough. Just come back here let the y disappear. You got x equals -1. If you let x equal 0, then you have a factorable expression, y cubed minus 1 equals 0. And that's the difference of cubes, so remember how to factor that. That's the quantity y minus 1, and y squared plus 1y plus 1. We get a y equals 1, okay? Out of this, I should have over here 1. I have -1. That's supposed to be +1, mind you. Okay? And this expression, this quadratic, will not have any solutions. You can trust me on that. So what does it look like? Well, it has no symmetry, and it crosses the x-axis at -1 and the y-axis at +1. Well, and again, since this is written x in terms of y, you can't ask your calculator to graph that. But I offered you that option over here, and let's take a look at it from here, okay? So what we're asked to graph here is the expression, try to remember, x equals y cubed minus 1, okay? So x equals y cubed minus 1, I'm going to key that in. X equals y raised to the third power minus 1. Again, we did not see any symmetry with this. Let's see what the graph looks like, okay? And say the graph then, okay, here's the graph. The graph has the intercepts we called for, 1 on the x-axis, I'm sorry, 1 on the y-axis, -1 on the x-axis, just as we had suspected it would be. There's the intercepts, -1, 0, and 0, 1. Again, there's your graph, and again, I'm not necessarily expecting that you can generate that graph, but at least use the ideas of what you were looking for. That is the fact that it has no symmetry and you have the intercepts to help. Okay. Next, we look at this expression. Okay, the absolute value of x plus y equals 2. Here's the intercepts are easy to find. So if x equals 0, then we left with absolute value of y equals 2, which means y could equal -2 or +2. So effectively, we have 2 y-intercepts. The same rationale, if y were equal to 0, you're left with absolute x equals 2, which again offers you -2 or +2 as your intercepts on the x-axis. So we're looking at 2 x-intercepts, 2 y-intercepts. The symmetry on this might be interesting. We're going to start by replacing x with its opposite, -x, okay? And I do that right here. And now I'm trying to see if I can, if this can be forced back to what it was originally. And I said -x minus, -x plus y is equal to 2. You might be able to draw a conclusion that's not the same by any means, okay? There are some properties of absolute values. They were discussed earlier in chapter 1. You might want to look at these. What I did is actually said, well, I can pull out a -1. That reveals here the x minus y in the inside. And then since this whole thing is -1, I can, as an opposite or negative is a common factor, I can write it as -1. And then there's an absolute value property that says the absolute value of A times the absolute value of B is equal to the absolute value of A times B. So that's kind of what I applied there, and in doing that, I'm not back to the original. So therefore, we don't get the symmetry with respect to the y-axis by replacing x with its opposite. I think you might reason that the same thing would happen if you replace y with its opposite. You're not getting back the original. However, if we replace both x and y with their opposites, as we're showing here, okay, then you got that negative common factor coming out. Then we're using this property of absolute values again, okay, and we are coming back to the original. So interestingly enough, that concludes that there is symmetry to the origin. So we've got origin symmetry. We got the graph intercepting the x-axis at 2 and -2, and intercepting the y-axis at the same values. It'd be interesting to take a look at this. Again, we can't ask our calculator, but we can ask this program that I provided for you. So let's take a look. So we're going to ask this to say absolute value, that's ABS, parenthesis, x plus y, okay? And that's supposed to equal 2, right? Okay, now let's take a look at that as a graph, okay? And here it is, okay? Looks like two parallel lines, exactly. Okay, intercepting at -2 and -2 on the x and y, intercepting at 2 and 2. Well, that's just as we called it, okay? And there is symmetry about the origin, okay? A test, I mean, it contains, if it contains, let's say 1, 1 looks like it contains, and it also contains -1, -1. The graph here contains the point -1, 3. So this graph contains the opposite of both, 1, 3. So you do have that symmetry, okay, as we determined, and we do have that those intercepts as we determined as well. Interesting graph, okay? So there you have a couple examples. Use those as guidelines for solving your the other problems you have.